Hello and welcome to the Deep Space Relax channel. I'm really glad you're here. Maybe today was long and tiring, or maybe you're someone who prefers falling asleep thinking about faraway planets and drifting moons rather than counting sheep. Either way, tonight's journey is meant just for you. You don't need to do anything now except rest. Let your breathing slow down, let your thoughts soften, and allow your body to feel lighter, as if gravity has relaxed its hold and you've begun to float gently through space. Tonight, we'll drift calmly through the solar system, not in a straight path, but in slow, graceful spirals, moving from sunlit planets and dusty rings to shadowed craters and frozen oceans hidden beneath layers of ice. This is a story told not with numbers, but with magnetic storms, tilted axes, and moons that glow softly in the dark. From sideways worlds and falling diamonds to ancient sunlight still traveling across the void, every orbit holds something strange and beautiful. We'll move slowly and gently, one sleepy fact at a time. And before we begin, if these quiet explorations help you relax or give you a peaceful way to end your day, you might consider softly tapping the like button and subscribing to the channel. It helps other sleepy souls find their way here as well, one gentle moment at a time. Now, let's begin. Neptune's winds move faster than sound. Even though it's the most distant known planet from the Sun, Neptune has the fastest winds in the entire solar system. These powerful winds race through its upper atmosphere at speeds exceeding 2,000 kilometers per hour, faster than the speed of sound on Earth. That's roughly 5 times faster than a commercial airplane. Scientists believe these winds are powered by heat rising from deep inside the planet, energy that continues to escape despite the extreme cold at the surface. Neptune's atmosphere is made mostly of hydrogen, helium, and methane, and the winds sculpt massive storm systems into its pale blue clouds. It's a frozen world in constant supersonic motion. Mars contains a canyon the size of a continent, stretching more than 4,000 kilometers across the Martian equator. Valles Marineris is the largest canyon system in the solar system. It would span the entire width of the continental United States. In some places, it drops more than 7 kilometers deep, over 5 times deeper than the Grand Canyon. Scientists believe it formed through a mix of tectonic stretching, volcanic activity, and erosion. Unlike canyons on Earth, which are often carved by flowing rivers, this vast chasm likely opened as the planet's crust fractured and pulled apart. It remains a massive scar on Mars's surface, a reminder of a violent geological past now locked in time. Venus has no global magnetic field. Despite being similar to Earth in size, mass, and overall composition, Venus lacks a crucial planetary feature, a strong magnetic shield. On Earth, our magnetic field is created by the movement of molten iron in the outer core, protecting the planet from harmful solar radiation. Venus, however, appears to have a slow-moving or possibly solid core, preventing the dynamo effect needed to generate a magnetic field. Without this protection, Venus's atmosphere has been steadily battered by the solar wind, which stripped away lighter elements over time. The absence of a magnetic field helps explain how Venus, once potentially Earth-like, transformed into the scorching furnace we see today. Diamonds may fall like rain on Uranus and Neptune. Deep within the atmospheres of Uranus and Neptune, conditions may be extreme enough to create something remarkable: falling diamonds. These icy giants contain thick layers of methane gas, and under immense pressure and heat, scientists believe the methane breaks apart, freeing carbon atoms. Those atoms may compress into crystalline structures, forming tiny diamonds that drift downward toward the planet's cores. Laboratory experiments have recreated similar conditions, showing how hydrocarbons can transform into diamond under the right pressures. If this process truly occurs, storms of glittering crystals may quietly descend through the deep blue darkness of these distant worlds. Earth is the only planet known to have plate tectonics. One of Earth's most distinctive and life-supporting features is its system of plate tectonics, a dynamic network of shifting crustal plates floating atop the mantle. These moving plates cause earthquakes, build mountains, and recycle carbon dioxide, helping regulate the planet's climate over geological time. So far, no other planet has shown clear evidence of this process. Mars and Venus display surface fractures and volcanic features, but they appear largely geologically inactive by comparison. Earth's plate tectonics may be a key reason the planet remains habitable, driving long-term cycles that stabilize temperatures, sustain oceans, and move continents across eons. Some asteroids have their own moons. While asteroids are often imagined as solitary travelers, some of them actually have small moons orbiting nearby. These tiny companions may be captured fragments or bodies that form together. The first known asteroid moon, Dactyl, was discovered orbiting asteroid Ida by the Galileo spacecraft in 1993. Since then, many more asteroid moon systems have been identified, including binary pairs where two asteroids circle one another. These miniature systems show that even the smallest objects in space can be bound together by gravity, forming quiet partnerships drifting through the solar system. Mercury has a ghost-like exosphere instead of a true atmosphere. Unlike Earth, Mercury lacks a thick atmosphere capable of holding heat or scattering sunlight. Instead, it is surrounded by a very thin cloud of particles called an exosphere, a near vacuum where atoms rarely collide. This exosphere forms from atoms blasted off the surface by solar wind and micrometeoroid impacts, including sodium, potassium, and oxygen. Because Mercury's gravity is too weak to hold on to these particles, they constantly escape into space and are continuously replaced. The result is a faint, shimmering envelope of atoms, invisible to human eyes, but detectable with specialized instruments. The Sun loses millions of tons of mass every second. Each second, the Sun converts more than 4 million tons of its own mass into energy through nuclear fusion. Deep in its core, hydrogen atoms fuse into helium, releasing enormous amounts of light and heat. That energy radiates outward, warming planets, driving winds, and supporting life on Earth. Although this loss is tiny compared to the Sun's total mass, over billions of years, it adds up. One day, the Sun will exhaust its hydrogen fuel and begin to change. For now, it continues to burn steadily, giving up a small part of itself with every passing second. Saturn's rings are slowly disappearing. The stunning rings that surround Saturn are not permanent. Over time, they are gradually falling into the planet, pulled inward by gravity and guided by Saturn's magnetic field. This process, known as ring rain, involves streams of icy particles and charged material drifting down toward the planet. Data from the Cassini spacecraft suggests the rings may be less than 100 million years old and could disappear completely within a few 100 million years. Though they appear timeless, Saturn's rings are temporary, a brilliant display that will one day fade. Mars experiences planet-wide dust storms. Mars is famous for its rust-colored deserts and for massive dust storms that can sometimes spread across the entire planet. These storms may last for weeks or even months, blocking sunlight and reshaping the surface beneath them. The dust is extraordinarily fine and can remain suspended in the air, forming a soft, reddish haze across the sky. Some storms start as gentle gusts, but can quickly intensify through feedback between heat, wind, and surface features. In 2018, one such storm brought the Opportunity rover's mission to an end when its solar panels were covered in dust. Even without rain or seas, Mars is still an active, unsettled world. Europa may hide a salty ocean beneath its ice. Below the frozen crust of Jupiter's moon Europa, strong evidence points to a vast underground ocean of liquid water. Gravitational tides from Jupiter flex Europa's interior, producing heat that may prevent the ocean from freezing completely. The surface is streaked with dark lines and ridges, signs of shifting ice, and spacecraft have detected magnetic signals and chemical traces that support the ocean theory. What makes Europa especially compelling is the chance that this hidden sea could support life. It is a dark, alien ocean, warmed from below, sealed under ice, yet potentially rich in the ingredients for biology. Mars has a volcano taller than Everest. Olympus Mons, the largest volcano in the solar system, rises nearly 22 kilometers above the Martian plains, almost 3 times taller than Mount Everest. It is so broad that it would cover the entire state of New Mexico. Built by repeated eruptions over millions of years, Olympus Mons grew enormous in part because Mars lacks plate tectonics. On Earth, volcanic hotspots move over time, forming chains like Hawaii. On Mars, the crust stays still, allowing magma to erupt in the same place again and again. The result is a single, colossal shield volcano, standing silently in the Martian night. Saturn's rings are paper-thin. Saturn's magnificent rings stretch more than 280,000 kilometers across, yet they are astonishingly thin. In many regions, the rings are less than 100 meters thick, thinner than many city buildings. Made mostly of water ice, the ring particles range from dust-sized grains to boulders as large as houses. When sunlight passes edge-on through the ring plane, they nearly vanish from view like a sheet of glass turned sideways. Their flat shape is maintained by Saturn's gravity, the self-organization of billions of icy fragments, and the influence of small shepherd moons. From afar, they seem solid, but up close, they are delicate and ethereal. Earth is the densest planet. Of all the planets in the solar system, Earth has the greatest density. This means it packs more mass into each cubic kilometer than any other planet, thanks to its metal-rich core and silicate mantle. Earth's average density is about 5.5 grams per cubic centimeter, higher than Jupiter's, despite the gas giant's immense size. This high density helps generate Earth's magnetic field, produced by the movement of molten iron in the outer core. Our planet's interior is compact, heavy, and layered, shaping not only its gravity, but its geology and protection from space. The sun vibrates like a musical instrument. Although we cannot hear it, the sun constantly resonates with pressure waves rippling through its blazing layers. These oscillations, caused by rising and falling currents of plasma, create ultra-low frequency vibrations far below human hearing. Scientists study these motions using a method called helioseismology. By tracking how waves move and bounce inside the Sun, researchers can map its internal structure, much like seismic waves reveal Earth's interior. These solar vibrations expose hidden flows, magnetic activity, and the dynamics of fusion deep in the core. In a sense, the Sun is always humming, quietly revealing its secrets through rhythm and motion. Venus rotates backward. Unlike most planets, Venus spins in the opposite direction, a phenomenon known as retrograde rotation. On Venus, the Sun rises in the west and sets in the east. Even stranger, the planet rotates extremely slowly. One Venusian day lasts longer than its year, taking 243 Earth days to complete a single rotation. Scientists are unsure why this happened, but one idea involves a massive early collision that altered its spin. Another suggests long-term tidal interactions with the Sun gradually reversed its rotation. Whatever the cause, Venus remains a slow-turning world with a reversed rhythm. Jupiter has more than 90 moons. Jupiter is not only the largest planet, but also the ruler of moons. Astronomers have identified more than 90 natural satellites orbiting it, and new ones are still being found. Its 4 largest moons, Io, Europa, Ganymede, and Callisto, are called the Galilean moons, named after Galileo Galilei, who first observed them in 1610. Beyond these giants lies a swarm of smaller, irregular moons, many captured from passing objects. Some orbit backward, some are only a few kilometers wide. Together, they form a miniature solar system bound by Jupiter's immense gravity and history. Mercury hides ice in its shadows. Scorching by day and freezing by night, Mercury seems an unlikely place for ice. Yet at its poles, deep inside craters that never receive sunlight, temperatures stay cold enough for water ice to survive. These permanently shadowed regions act as natural freezers, preserving ice for millions of years. Radar reflections from spacecraft like Messenger have confirmed these bright icy deposits. Scientists believe the water arrived through comet impacts or ancient volcanic outgassing. At the heart of one of the hottest planets, ice endures, locked in darkness and shielded from the Sun's relentless glare. Pluto's heart may conceal an ocean. The bright, heart-shaped region on Pluto, known as Sputnik Planitia, is more than a striking landmark. It may be the surface expression of a deep underground ocean. Although Pluto lies far from the Sun and is cold enough to freeze nitrogen, data from the New Horizons mission suggests liquid water could exist beneath its icy crust. The weight of the basin and signs of geological activity hint at a slushy, convecting interior. If this ocean exists, it may be kept liquid by radioactive heat and insulating layers of ice above. Even in the frozen outskirts beyond Neptune, a hidden sea may quietly persist. The asteroid belt is mostly empty space. Despite popular imagination, traveling through the asteroid belt would not resemble dodging rocks in a science fiction film. In reality, the belt is vast and sparsely populated. Located between Mars and Jupiter, it contains millions of rocky bodies separated by huge distances. A spacecraft could pass through without encountering a single obstacle. The total mass of the asteroid belt is less than 5% of the Moon's mass. Its largest members, like Ceres and Vesta, hold most of that mass. The rest are scattered fragments from the early solar system, ancient building blocks that never formed a planet. Uranus rolls around the Sun. Most planets spin like tops, tilted slightly on their axes. Uranus, however, is tipped so far over that it essentially rolls along its orbit with an axial tilt of 98 degrees. This means its poles point almost directly at the Sun during parts of its journey, creating extreme and unusual seasons. Each pole experiences about 42 years of continuous daylight, followed by 42 years of darkness. The cause of this tilt is still debated, but it may be the result of a massive ancient collision. Uranus's sideways orientation gives it one of the strangest climates in the solar system. Jupiter's radiation belts are deadly. Jupiter is wrapped in the strongest magnetic field of any planet, and within it lie radiation belts so intense they would quickly destroy unprotected spacecraft. These belts are filled with charged particles trapped by the magnetic field, forming zones of extreme radiation similar to Earth's Van Allen belts, but far more powerful. Jupiter's largest moons are exposed to this radiation as well, affecting their surfaces and potential habitability. To survive near Jupiter, spacecraft must use heavy shielding or carefully chosen trajectories. It is a beautiful planet, but one surrounded by invisible danger. The Sun contains nearly all the mass in the solar system. At the center of the solar system, the Sun dominates not only with light and gravity, but with sheer mass. It holds more than 99.8% of all the mass in the system. Everything else, planets, moons, asteroids, comets, and dust, adds up to less than 1/4%. The Sun's gravity binds objects from tiny grains in the asteroid belt to distant comets in the Oort cloud. This immense mass fuels the fusion reactions in its core, converting hydrogen into helium and flooding space with energy every day. There are more dwarf planets than classical planets. Beyond Neptune lies a scattered population of icy objects, many large enough to be classified as dwarf planets. Pluto is the most famous, but it is only one of many. Others like Eris, Haumea, and Makemake share this status, with more candidates continually discovered in the Kuiper Belt and beyond. In fact, dwarf planets may far outnumber the 8 classical planets. These small, rounded worlds are ancient relics of the early solar system. Though they orbit in distant cold regions, they carry clues to how everything we know first formed. A day on Venus lasts longer than its year. Venus has one of the slowest rotations of any planet. It takes 243 Earth days to complete one spin on its axis, while it needs only 225 days to orbit the Sun. That means a single day on Venus, from one sunrise to the next, is actually longer than an entire year. This slow rotation also helps create brutal surface conditions, with temperatures hot enough to melt lead. With its thick, acidic atmosphere and crushing pressure, Venus becomes a world of lingering furnace-like heat and eerie, sun-dimmed days. Titan has lakes made of methane. Titan, Saturn's largest moon, is the only other place in the solar system known to have stable liquids on its surface, but they are not water. Instead, Titan's lakes and rivers are made of liquid methane and ethane, flowing across terrain shaped by cold chemistry. Its thick, nitrogen-rich atmosphere forms weather systems that include methane rain and even seasonal storms. Some of Titan's lakes are enormous, stretching hundreds of kilometers. Beneath the icy crust, scientists also suspect a subsurface ocean of water may exist. Titan is a world of familiar outlines, clouds, rivers, shorelines, built from utterly alien materials. The moons of Mars may be captured asteroids. Mars has 2 small misshapen moons, Phobos and Deimos. They look more like asteroids than typical moons, irregular, rocky, and cratered. Many scientists think they were once part of the asteroid belt and were captured by Mars's gravity long ago. Their odd orbits and low densities support this idea, though another possibility is that they formed from debris left after a massive impact. Phobos is slowly spiraling inward toward Mars and will one day break apart or crash into the planet. Deimos is drifting outward. These tiny moons are quiet passengers in orbit, leftovers from a turbulent past. Jupiter glows with its own heat. Unlike most planets, Jupiter gives off more energy than it receives from the Sun. This internal glow comes from leftover heat from its formation, gravitational energy released when the planet's immense mass collapsed. Over time, Jupiter continues to contract slightly, producing heat in the process. This warmth fuels Jupiter's turbulent weather, including giant storms and its banded atmospheres. In infrared light, Jupiter shines brightly, like a smoldering ember beneath its cloud tops. It is not a star, but it nearly became one. If it were just a little more massive, it might have ignited as a failed sun. Neptune was discovered through math. Unlike other planets, Neptune was not found by simply pointing a telescope at the sky. Astronomers noticed small irregularities in Uranus's orbit, tiny deviations that known gravity could not explain. Two mathematicians working independently in the 1840s used these strange motions to predict where a hidden planet should be. When astronomers aimed telescopes at the calculated position, Neptune was there. It was a triumph of celestial mechanics, proving unseen forces could be mapped with mathematics alone. Neptune was the first planet found on paper before it was seen through glass, a world revealed by numbers. Saturn's North Pole has a hexagon. At Saturn's North Pole, a giant cloud pattern spins in a near-perfect hexagon. This six-sided jet stream spans over 30,000 kilometers, wider than Earth, and has persisted for decades, possibly even centuries. Scientists think the hexagon forms from how Saturn's atmosphere rotates and interacts with stable waves of air trapped around the pole. In laboratory experiments, similar shapes appear when rotating fluids move at different speeds. The fact that such a clean geometric figure can emerge naturally in a planetary atmosphere remains one of the solar system's most surreal and elegant phenomena. The Sun's atmosphere is hotter than its surface. It seems intuitive that the Sun's surface should be the hottest part, but it is not. The visible surface, the photosphere, has a temperature of about 5,500 degrees, yet the outer atmosphere, called the corona, can exceed 1,000,000 degrees. This surprising temperature rise has puzzled scientists for decades. One theory suggests magnetic waves from within the Sun carry energy upward, heating the corona from below. Another involves countless tiny solar blasts called nanoflares. Either way, the Sun's outer layers blaze with a mysterious, searing heat far beyond what seems possible. The Kuiper Belt is full of icy worlds. Beyond Neptune lies a broad ring of frozen objects known as the Kuiper Belt. It stretches billions of kilometers from the Sun and holds countless icy bodies, including Pluto, Eris, Haumea, and Makemake. These are not stars or full planets, but ancient leftovers from the solar system's formation. Some are round enough to be classified as dwarf planets, while others are irregular, tumbling through space. The Kuiper Belt resembles the asteroid belt in structure, but it is far colder and far richer in primordial ice. It is a fossil zone, a frozen archive of the materials that built the outer worlds. The Oort cloud may stretch a light year from the Sun. Far beyond the Kuiper belt, beyond even Pluto's most distant reach, lies a hypothetical shell of icy bodies known as the Oort cloud. Though never observed directly, this vast sphere of frozen debris is thought to surround the solar system and extend nearly a light year away. It is the likely source of long-period comets, visitors that arrive from deep space on unpredictable paths. These distant objects are only weakly bound to the Sun, and a passing star or the pull of the galaxy could send one plunging inward. If the Oort cloud exists, it marks the true edge of the Sun's gravitational reach, a remote halo of icy wanderers. Io is the most volcanic world in the solar system. Jupiter's moon Io is a seething, restless world covered with active volcanoes. Its surface is constantly rebuilt by eruptions of molten sulfur and rock, painting the landscape in vivid yellows, reds, and blacks. Some volcanic plumes rise hundreds of kilometers into space. This extreme activity is powered by tidal heating. Io is squeezed and stretched by Jupiter's gravity, along with tugs from neighboring moons. The friction from this constant flexing heats the interior, driving its furious geology. Unlike Earth's cooling crust, Io's surface is young, volatile, and ever-changing. A lava-lit moon with a molten heart. Triton orbits backward around Neptune. Triton, Neptune's largest moon, is unusual among large moons because it orbits in the opposite direction of Neptune's rotation, a motion called a retrograde orbit. This backward path suggests Triton did not form beside Neptune, but was likely captured from the Kuiper belt. That capture may have caused dramatic upheaval, possibly disrupting Neptune's original moon system. Triton is also geologically active, with cryovolcanoes that spray icy material and a thin atmosphere that fades and returns with the seasons. Cold, distant, and moving in reverse, Triton is a world that defies expectation at every turn. Earth's moon is unusually large. Compared to its planet, Earth's moon is enormous. No other rocky planet has such a relatively large satellite. The moon is about 1/4 of Earth's diameter, a ratio more typical of dwarf planet systems than full-sized planets. Most scientists think it formed when a Mars-sized body struck the young Earth, sending debris into orbit that later clumped together into the moon. This close partnership has shaped Earth's tides, climate, and stability for billions of years. Our moon is not just a companion, it is a cosmic legacy of collision and renewal. Planetary orbits are not perfect circles. Although we often imagine planets moving in perfect circles around the Sun, their paths are actually ellipses, slightly stretched circles with the Sun off-center. This means every planet has a closest point, called perihelion, and a farthest point, called aphelion. For many planets, the difference is small, but for others, like Mercury and Pluto, it is more dramatic. These shifts affect seasons, solar radiation, and orbital speed. The elliptical nature of planetary motion was first described by Johannes Kepler in the 1600s, reshaping our view of the solar system's graceful mechanics. Some comets come from the edge of interstellar space. Long-period comets, those that appear only once every few thousand years, are believed to come from the Oort cloud, a faraway shell of icy debris that may stretch nearly a light year from the Sun. These comets travel on elongated, weakly bound orbits and are often dislodged by passing stars or galactic tides. When they fall inward, they can flare into brilliant tails visible from Earth. Some may have drifted in darkness for billions of years before being nudged into motion. Their bright returns are brief glimpses of the solar system's oldest, most untouched matter. The Sun will become a white dwarf. The Sun, like all stars, has a finite life. In about 5 billion years, it will use up the hydrogen fuel in its core and swell into a red giant, possibly engulfing the inner planets. After shedding its outer layers in a glowing shell of gas called a planetary nebula, the remaining core will become a white dwarf, a dense, Earth-sized remnant made mostly of carbon and oxygen. This white dwarf will no longer generate energy and will slowly cool over trillions of years. It will be the Sun's final form, a fading ember in the dark at the end of its stellar journey. Mars has seasons like Earth. Though colder and with a thinner atmosphere, Mars experiences seasons much like ours because it has a similar axial tilt, about 25 degrees compared to Earth's 23. As Mars orbits the Sun, this tilt makes sunlight strike each hemisphere more directly at different times, creating spring, summer, autumn, and winter. Martian seasons also influence the polar caps, dust storms, and even subtle shifts in air pressure. They unfold more slowly than Earth's seasons because Mars takes nearly twice as long to complete a year. Ganymede is the largest moon in the solar system. Jupiter's moon, Ganymede, is the largest natural satellite in the solar system, even bigger than Mercury. With a diameter over 5,000 kilometers, Ganymede has a rocky core, a possible underground ocean, and an icy crust marked by ridges and ancient scars. It is the only moon known to have its own magnetic field, producing shimmering auroras in its thin atmosphere. Scientists suspect Ganymede may contain multiple ocean layers trapped between sheets of ice, forming a complex interior world. Despite its size and richness, it remains quiet and dark, orbiting deep within Jupiter's magnetic grip. Pluto sometimes orbits closer to the Sun than Neptune. Although Pluto is usually the most distant of the classical and dwarf planets, its orbit is highly elliptical, meaning it can sometimes travel closer to the Sun than Neptune does. This happened between 1979 and 1999, when Pluto was temporarily the 8th planet from the Sun instead of the 9th. Even so, Pluto and Neptune never collide because their orbits are locked in resonance. For every 3 orbits Neptune completes, Pluto completes exactly 2. This gravitational choreography keeps their paths stable, a careful dance where their tracks never truly meet. The Sun reverses its magnetic field every 11 years. Roughly every 11 Earth years, the Sun's magnetic field flips, swapping north and south magnetic poles. This process, called the solar magnetic cycle, is tied to the Sun's internal motion and affects solar activity, including sunspots, flares, and coronal mass ejections. At the peak, known as solar maximum, the Sun becomes more active, throwing stronger magnetic storms and radiation into space. As the cycle fades, activity drops towards solar minimum. These cycles influence Earth's upper atmosphere, satellites, and auroras. The Sun's magnetism is not fixed. It pulses and shifts like a slow magnetic heartbeat. Planetary alignments don't cause natural disasters. It is a common myth that alignments of planets trigger earthquakes, floods, or other catastrophes on Earth. But there is no scientific evidence supporting this idea. The gravitational pull of other planets on Earth is tiny compared to the Moon or the Sun. Even during rare alignments, their combined influence is negligible. The Moon, because it is close, has far more impact on tides and small stresses than distant giants like Jupiter or Saturn. Alignments are visually beautiful and mathematically interesting, but gravitationally harmless, a silent choreography of distant worlds, not a cosmic omen. Leaving the solar system takes decades. Escaping the sun's gravitational hold is not easy. Spacecraft like Voyager 1 and Voyager 2, launched in the 1970s, only entered interstellar space decades later, the region beyond the heliopause, where the solar wind gives way to the interstellar medium. These missions took more than 40 years to reach that boundary, traveling outward at speeds above 60,000 kilometers per hour. The Voyager probes crossed planetary orbits, passed through the Kuiper Belt, and continued into the dark. They still carry working instruments and a golden record filled with sounds of Earth. They are our quiet ambassadors to the galaxy. Earth's magnetic field shields us from space radiation. Around our planet is an invisible magnetic field generated by the movement of molten iron in Earth's outer core. This field deflects charged particles from the sun, protecting the atmosphere and surface from harmful solar and cosmic radiation. Without it, the solar wind would slowly strip away our atmosphere, as it likely did on Mars. The field also channels some particles toward the poles, where they collide with atmospheric gases and create auroras, shimmering curtains of green, red, and violet light. Earth's magnetosphere is a dynamic shield essential for sustaining both life and climate over geologic time. The moon is slowly moving away from Earth. Each year, the moon drifts about 3.8 centimeters farther from Earth. This gradual retreat is caused by tidal interactions. Earth's pull creates bulges in the oceans, and that interaction transfers energy that nudges the moon outward. Long ago, the moon was closer and appeared much larger in the sky. As it recedes, Earth's days slowly lengthen, and total eclipses will eventually become rarer and less dramatic. Billions of years from now, the moon will be so far away that total solar eclipses may no longer happen at all. The sky is changing, even if we cannot yet feel it. The Kuiper Belt holds icy worlds with mirrored surfaces. Far beyond Neptune, the Kuiper Belt holds not only dwarf planets, but also smaller icy bodies with strikingly bright surfaces. One example is Haumea, a fast-spinning, football-shaped object coated in crystalline water ice. Another, Eris, reflects nearly all the sunlight that reaches it, making it one of the most reflective bodies in the solar system, brighter than freshly fallen snow. These objects may have been resurfaced by cryovolcanism, impacts, or chemical interactions. In the darkness at the edge of the sun's reach, some of these distant worlds shine like cold mirrors, catching faint sunlight in their frozen silence. Enceladus sprays water into space. Saturn's tiny moon. Enceladus may be small, but it hides a spectacular secret. From its south pole, towering geysers of water vapor and ice crystals burst into space through cracks known as tiger stripes. These plumes are powered by tidal heating beneath the surface, where friction from Saturn's pull keeps a subsurface ocean in a liquid state. The material in the plumes contains organic compounds, salts, and even signs of hydrothermal activity, raising the tantalizing possibility of life. Some of the water escapes into space and helps replenish Saturn's E-ring, forming a living connection between moon and planet. Some asteroids are just piles of rubble. Not all asteroids are solid rock. Many are loose collections of stones, gravel, and dust, held together only by gravity. structures known as rubble piles. These fragile bodies can form after collisions shatter larger asteroids, with the debris slowly gathering again over time. Rubble pile asteroids can contain large internal voids, spin in odd ways, and even change shape under stress. Missions like Hayabusa 2 and OSIRIS-REx have visited such bodies, confirming their delicate, porous nature. These asteroids are not monolithic relics, but chaotic assemblages, ancient drifting ruins of early planetary construction that barely hold themselves together as they orbit the Sun. Mercury's core is disproportionately large. Mercury is a small planet, yet it has an unusually massive iron core. This metallic center makes up about 80% of the planet's radius, a far larger fraction than in Earth or Venus. The reason for this oversized core remains uncertain. Some scientists think Mercury once had a thick, rocky mantle that was stripped away by a giant impact. Others believe it formed close to the Sun, where solar forces favored the buildup of heavier elements. The result is a planet with a thin crust, a huge core, and a weak magnetic field, a metal-heavy survivor from the solar system's chaotic youth. Venus has no moons at all. Among the rocky planets, only Mercury and Venus have no natural satellites. While Mercury's closeness to the Sun may help explain its lack of moons, Venus's situation is more puzzling. It is roughly Earth size, and Earth has a large moon, yet Venus has none. Some theories suggest Venus may have once had a moon that fell back into the planet or was lost in a collision. Others argue that Venus's slow, retrograde spin might prevent stable satellite orbits from forming. Whatever the cause, Venus travels alone, a bright, cloud-wrapped world with no lunar companion in its twilight sky. Most of the solar system's moons orbit gas giants, while Earth has only one moon and Mars has two tiny ones. The giant planets of the outer solar system are surrounded by sprawling satellite systems. Jupiter and Saturn each have dozens of confirmed moons, ranging from tiny captured asteroids to massive worlds like Ganymede and Titan. Uranus and Neptune also host many icy moons, some with complex orbits and hidden oceans. These gas giants act like miniature solar systems, their gravity drawing in debris and assembling satellites over time. The farther from the Sun you go, the more moons you tend to find, a reminder that gravity gathers companions in the cold. Hubble has photographed planets from Earth orbit. Though it circles just above Earth, the Hubble Space Telescope has captured detailed images of the outer planets, including cloud bands on Jupiter, storms on Neptune, and seasonal changes on Mars. These views provide long-term monitoring that complements spacecraft flybys, revealing evolving weather patterns, ring systems, and planetary auroras. Hubble's sharp vision lets scientists track storm growth, watch impact events, and study atmospheres in ultraviolet and visible light. From its quiet perch in low Earth orbit, Hubble observes not only distant galaxies, but also the changing faces of our neighboring worlds. Jupiter's Great Red Spot is centuries old. The Great Red Spot is a gigantic storm spinning in Jupiter's southern hemisphere, wide enough to swallow 2 or even 3 Earths. It has raged for at least 350 years, possibly far longer. First recorded in the 1600s through early telescopes, the storm has shifted over time, gradually shrinking, but still remaining powerful. Its reddish color may come from complex chemical reactions in Jupiter's atmosphere, driven by sunlight and high-altitude compounds. Wind speeds exceed 400 kilometers per hour along its outer edges. While storms on Earth last days or weeks, this Jovian tempest has persisted for centuries, trapped within the planet's turbulent belts. Neptune radiates more heat than it receives from the Sun. Although it lies far from the Sun, Neptune is not a frozen, inert world. In fact, it radiates about 2.6 times more energy than it absorbs. This internal heat helps drive strong winds and storm systems, including the fastest recorded winds in the solar system. The exact source of Neptune's heat is uncertain, but possibilities include leftover energy from formation, slow gravitational contraction, or radioactive decay within its interior. Despite its extreme distance, Neptune is a planet of surprising energy, a world with a cold exterior and a warm, restless interior that constantly reshapes its windswept atmosphere. Earth is the only planet with water in all three states. Our planet is unique in that water exists naturally on its surface as solid, liquid, and gas. Ice caps and glaciers, oceans and lakes, clouds and vapor all coexist and cycle through atmosphere, land, and sea. This balance is crucial for life and is regulated by Earth's distance from the Sun, its atmospheric pressure, and its relatively stable climate. Other worlds may hold water in isolated forms, ice crusts, vapor in thin skies, or hidden subsurface oceans, but none show the same dynamic, planet-wide presence. On Earth, water flows, freezes, and evaporates in a never-ending, life-sustaining dance. The heliopause marks the edge of the Sun's influence. As the solar wind streams outward from the Sun, it eventually collides with the interstellar medium, the thin gas and dust between stars. This boundary is called the heliopause, and it defines the outer edge of the Sun's protective bubble, the heliosphere. Beyond this point, pressure from galactic particles and other stars becomes stronger than the solar wind. Voyager 1 crossed the heliopause in 2012, followed by Voyager 2 in 2018, entering true interstellar space. Though the Sun's gravity reaches much farther, the heliopause marks the end of its energetic reach, the final breath of solar influence before deep space begins. The solar system is drifting through a local cloud. Our entire solar system is moving through a region of space called the local interstellar cloud, a thin concentration of gas and dust about 30 light-years across. It is part of a larger structure known as the local bubble, shaped by ancient supernova explosions. As the Sun travels through this cloud at about 7,000 kilometers per hour, its heliosphere acts like a shield, deflecting interstellar material. Scientists study this cloud to understand how interstellar conditions can affect cosmic rays, the heliosphere's shape, and even Earth's climate. We are not stationary in space. We are sailing slowly and silently through a faint galactic fog. Some moons are geologically active. Activity is not limited to planets. Several moons in the solar system show signs of internal energy and surface change. Io, a moon of Jupiter, is riddled with active volcanoes fueled by tidal heating. Enceladus, orbiting Saturn, vents plumes of water vapor into space. Europa and Ganymede likely hide subsurface oceans stirred by internal warmth. Even distant Triton, Neptune's captured moon, shows signs of cryovolcanism, icy eruptions driven by shifting pressures below. These moons are not static ice balls. They are restless worlds with geology, chemistry, and perhaps even the potential for biology hidden beneath frozen shells. Pluto's atmosphere comes and goes. Though Pluto is small and cold, it has a thin atmosphere made mostly of nitrogen, with traces of methane and carbon monoxide. When Pluto moves closer to the Sun along its elliptical orbit, surface ices sublimate into gas, forming a hazy envelope that expands outward. But as it travels farther away, the atmosphere cools and collapses, freezing back onto the surface like frost. This cycle repeats over Pluto's 248-year orbit. During New Horizons flyby in 2015, Pluto's atmosphere appeared as a layered blue haze, a fleeting breath of warmth around a world that spends most of its time in deep cosmic winter. Temperatures at the Sun's core exceed 15 million degrees. Deep inside the Sun, at its center, temperatures climb to over 15 million degrees Celsius. Here, hydrogen atoms are squeezed under immense pressure until they fuse into helium, releasing tremendous energy. This fusion powers the Sun's light and heat, and ultimately supports life on Earth. Energy created in the core takes hundreds of thousands of years to reach the surface, scattering through dense layers of plasma. Once it escapes, it crosses space in a little over 8 minutes to reach us. The Sun's calm glow hides an unimaginably hot and violent heart. Uranus has a faint, tilted ring system. Though Saturn's rings are the most famous, Uranus also has rings. 13 known ones, though they are darker and far fainter. Made of tiny particles of rock and ice, these rings orbit in alignment with Uranus's extreme tilt. Because the planet lies nearly on its side, the rings can appear almost vertical when viewed from certain angles. Some rings are narrow and sharp-edged, likely shaped by small shepherd moons that maintain their structure. They were not discovered until 1977, when they briefly blocked the light of a background star. They are subtle, shadowy bands circling a sideways planet. The heliosphere is a magnetic bubble blown by the Sun. The solar wind, a stream of charged particles released by the Sun, flows outward in all directions, forming a vast magnetic bubble around the solar system. This structure is called the heliosphere, and it acts as a shield against galactic radiation. Shaped by solar activity and interstellar pressure, it stretches far beyond Pluto, enclosing planets, comets, and distant objects. Its outer edge is the heliopause, where solar influence fades. As the Sun orbits the Milky Way, the heliosphere travels with it, guarding the solar system as it moves through changing regions of interstellar space. Mercury's orbit helped prove Einstein's theory of gravity. For centuries, astronomers noticed something odd about Mercury's path. Its closest point to the Sun, called perihelion, slowly shifted over time, more than Newtonian physics could explain. In 1915, Albert Einstein's general relativity provided the missing answer. In relativity, massive objects like the Sun warp the fabric of space-time, subtly altering planetary motion. The small but measurable effect on Mercury's orbit matched Einstein's predictions precisely. This became one of the first experimental confirmations of his revolutionary theory, a triumph of mathematics that explained a strange quirk in the motion of a scorched rocky world. The moon shapes Earth's tides. The daily rise and fall of ocean tides on Earth are driven largely by the moon's gravitational pull. As the moon tugs on Earth's oceans, it creates bulges on the side facing the moon and on the opposite side. As Earth rotates, these bulges sweep around the globe, producing high and low tides. The Sun also affects tides, creating spring and neap tides depending on how it lines up with the moon. Tidal forces do more than move water. They can subtly flex Earth's crust and even influence the planet's rotation over time. The moon's silent pull, keeps the oceans in motion. There may be undiscovered planets beyond Neptune. Astronomers have noticed that some distant objects in the Kuiper belt follow clustered, elongated orbits that are difficult to explain using only the known planets. One leading idea is that a large, still undetected world, sometimes called Planet 9, may be shaping those faraway paths with its gravity. If it exists, this hidden planet could be several times Earth's mass and orbit far beyond Pluto, taking thousands of years to complete a single revolution. No direct evidence has confirmed it yet, but telescopes continue searching. If found, it would reshape our understanding of the solar system's outer architecture. Callisto may have an ocean beneath its icy surface. Jupiter's moon, Callisto, looks quiet and heavily cratered, its ancient surface seemingly untouched by recent geological activity. But deep under that frozen crust, scientists suspect a subsurface ocean could exist, kept liquid by internal heating, and perhaps leftover warmth from formation. Magnetic measurements from the Galileo spacecraft hinted at a conductive layer beneath the surface, consistent with salty water. If confirmed, Callisto would join Europa and Ganymede as another ocean world. Though less famous, Callisto's deep, dark sea could hold ingredients for life, silently sealed beneath ice and time. Venus is hotter than Mercury, despite being farther from the Sun. Although Mercury is closest to the Sun, Venus has the hottest surface temperatures. The reason is its extraordinarily thick atmosphere, made mostly of carbon dioxide, which traps heat in a runaway greenhouse effect. Surface temperatures on Venus exceed 460 degrees Celsius, hot enough to melt lead. The dense clouds reflect sunlight, but they also prevent heat from escaping. Mercury, meanwhile, with its thin exosphere, lacks that insulation and cools quickly on its night side. Venus's searing heat isn't just about distance from the Sun. It's about atmosphere and the power of trapped radiation. The rings of Saturn are made mostly of ice. Though they shine like solid bands, Saturn's rings are made of countless individual particles, mostly water ice, ranging from dust grains to house-sized chunks. These icy fragments orbit in an incredibly thin, flat disk, held in place by Saturn's gravity and shaped by the influence of nearby moons. The ice gives the rings their bright reflectivity, making them one of the most luminous features in the solar system when seen from afar. Within the rings are narrow gaps, rippling wave patterns, and delicate ringlets sculpted by gravitational resonances. The rings are dynamic, ever-changing structures, carved ice caught in motion. Ceres is both an asteroid and a dwarf planet. Located in the asteroid belt between Mars and Jupiter, Ceres is the largest object in that region, so large that it qualifies as a dwarf planet. Discovered in 1801, Ceres is spherical unlike most smaller asteroids, and it may contain a subsurface layer of briny water or mud. NASA's Dawn spacecraft revealed mysterious bright spots on its surface, later identified as salt deposits, possibly left behind by evaporating water. Ceres is a hybrid world, neither fully planet nor typical asteroid, offering a glimpse into the early ingredients of planetary formation. Mars appears red because of rust. The surface of Mars is coated in fine dust, rich in iron oxide, the same compound that gives rust its color. Over billions of years, this iron-rich material oxidized in the thin Martian atmosphere, creating the planet's signature reddish hue. The dust is so widespread that it tints the sky during storms and coats nearly everything. Despite the rusty look, Mars also has dark basaltic plains, and polar ice caps, creating subtle color variations across its surface. But from far away, the distinctive red tone dominates, a dusty signal of oxidation on a cold desert world. Some spots are cooler regions on the sun's surface. Although the sun's surface blazes at thousands of degrees, some areas look darker, not because they are cold, but because they are cooler than the surrounding regions. These are sunspots, temporary patches where intense magnetic activity suppresses the outward flow of heat. Sunspots can be larger than Earth and often appear in pairs or clusters. They follow an 11-year cycle, becoming more common and active as the sun approaches solar maximum. Despite their name, they are still extremely hot, thousands of degrees. Yet the contrast makes them appear dark. These spots are magnetic scars, revealing the sun's ever-changing internal rhythms. Uranus was discovered by telescope. Unlike the planets known since ancient times, Uranus was not officially identified until 1781, when astronomer William Herschel observed it through a telescope. At first, he thought it might be a comet or a star, but further observations confirmed its planetary motion. Uranus became the first planet discovered in modern times, expanding the known boundaries of the solar system. Its discovery marked a turning point from naked eye astronomy to instrument-based exploration. Since then, Uranus has revealed many surprises, from its extreme axial tilt to its faint rings and icy moons. It is a planet that quietly rewrote the map of the night sky. The solar system is about 4.6 billion years old. By studying ancient meteorites, radioactive isotopes, and the oldest rocks on Earth and the Moon, scientists estimate the solar system's age at about 4.6 billion years. It began as a swirling cloud of gas and dust, a solar nebula that collapsed under its own gravity, forming the sun at its center. The remaining material then gathered into planets, moons, asteroids, and comets. This process of accretion and differentiation laid the foundation for everything that followed. The planets we see today are survivors of a chaotic beginning shaped by collisions, migrations, and long, slow cooling. Vesta has a layered structure, like a planet. Vesta, the second largest object in the asteroid belt, is not just a rock. It is a protoplanet with differentiated layers. Beneath its surface lies a mantle and a dense metallic core, similar to the internal structure of Earth and other terrestrial planets. This means Vesta once had enough internal heat to melt and separate into layers, a process known as planetary differentiation. The giant impact that carved the Rhea Silvia crater at its south pole may have exposed some of these deeper layers. Vesta is a frozen fossil, a planetary building block that never quite reached full planet status. The Moon has quakes. Though it looks still and silent, the Moon occasionally trembles. These moonquakes can be triggered by tidal forces from Earth's gravity, thermal expansion as the lunar surface heats and cools, or meteorite impacts. Some quakes originate deep inside the Moon and can last up to an hour, far longer than most earthquakes on Earth. Apollo mission instruments first revealed these subtle shakes, and newer tools continue to study them. Even without tectonic plates, lunar quakes suggest an interior that is not entirely dormant, a solid world with a quiet, pulsing heart. Triton is a captured moon. Neptune's largest moon, Triton, is unique among major moons because it orbits opposite to its planet's rotation in a retrograde path. This unusual motion suggests Triton did not form around Neptune, but was captured from the Kuiper Belt long ago. The disruption from that capture may have destroyed Neptune's original moons and affected Triton's interior, driving tidal heating. Today, Triton has geysers that blast nitrogen into space, a thin atmosphere, and a frozen surface marked by strange cantaloupe-like textures. It is both a relic of the outer solar system and a moon reshaped by a violent adoption. Neptune has 14 known moons. Neptune, the farthest major planet from the Sun, is orbited by at least 14 moons, ranging from large and mysterious to small and irregular. The largest, Triton, holds most of the system's mass, but others like Proteus, Naiad, and Larissa follow eccentric and varied paths. Some are likely captured Kuiper Belt objects, while others may have formed from collisions or leftover debris. Most of these moons are icy and dark, reflecting very little sunlight. Their orbits offer clues to Neptune's turbulent past and possible planetary migrations. Together, they form a scattered family of companions around a planet drifting on the solar system's distant edge. The Parker Solar Probe is touching the Sun. Launched in 2018, NASA's Parker Solar Probe is the first spacecraft to fly directly into the Sun's outer atmosphere, the corona. It travels at extraordinary speeds, faster than any object humans have built, and endures temperatures of over 1,000 degrees Celsius. Protected by a carbon composite heat shield, the probe dives closer with each orbit, collecting data on the solar wind, magnetic fields, and energetic particles. Its mission is to solve long-standing puzzles like why the corona is hotter than the Sun's surface and how solar eruptions accelerate particles. In a sense, it isn't just observing the Sun, it is flying through it. Some meteorites on Earth came from Mars. Though Mars is millions of kilometers away, pieces of it have landed on Earth. These are Martian meteorites, rocks blasted off the Martian surface by powerful impacts, sent drifting through space, and eventually pulled into our atmosphere. Scientists identify them by matching their chemistry to measurements made by Mars rovers and orbiters. Some contain tiny bubbles of trapped Martian air and minerals shaped by water, offering direct clues to Mars's geological and chemical history. These wandering stones are natural samples from another world, delivered long before any spacecraft returned the favor. The Sun is mostly hydrogen and helium. About 70% of the Sun's mass is hydrogen, and most of the rest is helium. These two lightest elements dominate its composition and fuel nuclear fusion in the core. Under extreme heat and pressure, hydrogen atoms fuse into helium, releasing vast amounts of energy. The remaining 1 to 2% includes oxygen, carbon, nitrogen, and heavier elements forged in earlier generations of stars. Despite its brilliance and complexity, the Sun is fundamentally simple in makeup, a glowing sphere of primordial gases shaped by gravity and nuclear fire. Earth's tilt gives us seasons. Earth's axis is tilted about 23.5 degrees relative to its orbit around the Sun, and this tilt is why we have seasons. When one hemisphere leans toward the Sun, it receives more direct sunlight and longer days, creating summer. When it tilts away, the sunlight is weaker and days are shorter, bringing winter. Without this tilt, seasons would be faint, and Earth's climate would be far more uniform. The tilt shifts slightly over time due to gravitational nudges from the Moon and other planets, but it remains one of the quiet architects of life's seasonal rhythms. Jupiter's magnetosphere is the largest structure in the solar system. Jupiter's immense magnetic field stretches millions of kilometers into space, forming a magnetosphere so vast that, if visible, it would look larger than the Sun in the night sky. This field is powered by electrical currents in the planet's metallic hydrogen interior. Inside the magnetosphere, charged particles race along magnetic lines, creating intense radiation belts, huge auroras, and powerful electrical storms. The field captures particles from Io's volcanic eruptions and influences the environment around nearby moons. For spacecraft, the radiation is a serious hazard. For scientists, it is a laboratory for studying planetary magnetism at its most extreme. Planetary rings may be temporary, though they seem timeless. Planetary rings, like those around Saturn, Jupiter, Uranus, and Neptune, may be relatively short-lived on cosmic timescales. Rings can form from shattered moons, leftover debris, or icy particles gathered into orbit. But over millions of years, that material can drift inward due to gravity, magnetic drag, or collisions, eventually raining down onto the host planet. Observations suggest Saturn's rings may be less than 100 million years old and could disappear within another 100 million. The rings we admire today may be a brief phase, an extraordinary shimmering moment in a planet's much longer life. The Moon's surface barely changes over time without wind, rain, or active geology. The lunar surface remains almost unchanged for millions, sometimes billions of years. Footprints left by astronauts will likely stay preserved for thousands of generations. Micrometeorites and cosmic radiation are the main forces that slowly wear down the landscape, causing a gradual erosion known as space weathering. Craters from ancient impacts still dominate the terrain, preserving a record of collisions reaching back to the solar system's earliest days. The Moon is not only Earth's closest neighbor, but also one of its oldest and most faithful geological archives. Some icy moons may have hydrothermal vents. Beneath the icy shells of moons like Europa and Enceladus, scientists think subsurface oceans could touch hot rocky cores, creating hydrothermal vents similar to those on Earth's ocean floor. On our planet, these vents support entire ecosystems without sunlight, powered by chemical energy from minerals and heated water. If similar vents exist on those moons, they could provide the key conditions for life: water, warmth, and a steady energy source. Plumes from Enceladus even contain compounds linked to biological processes. These hidden ocean worlds may be the most promising places to search for life beyond Earth. Sunlight takes over 8 minutes to reach Earth. The light that warms your skin and brightens the sky began its journey in the sun's core, where fusion produces photons. Those photons then take hundreds of thousands of years to work their way from the sun's center to its surface, bouncing and scattering through dense plasma. Once they finally escape, they cross the remaining distance to Earth, about 150 million kilometers, in just over 8 minutes. When you watch a sunrise or stare at the midday sun, you're seeing it not as it is, but as it was 8 minutes ago, a glimpse into the very recent past. Europa's cracked ice may shift like tectonic plates. The surface of Jupiter's moon Europa is coated in a shell of ice crisscrossed by dark lines, ridges, and chaotic terrain. These features suggest the ice could be moving, breaking, sliding, and perhaps even subducting, much like Earth's tectonic plates. If that's true, Europa would be the only known body besides Earth with active plate-like motion. Such movement could help cycle nutrients between the surface and the ocean below, boosting the moon's habitability. The driving force is likely tidal flexing from Jupiter's gravity, which constantly kneads Europa's interior. It's a frozen world, but not a motionless one. Saturn is less dense than water. If you could place Saturn in a gigantic cosmic bathtub, it would float. Not because it's hollow, but because its average density is lower than water's. Saturn is made mostly of hydrogen and helium, giving it a lightness despite its enormous size. Its volume is immense, more than 700 times Earth's, yet its mass is only about 95 times greater. This low density contributes to a soft, diffuse structure, and its rapid rotation flattens it at the poles and makes it bulge at the equator. It's a gas giant gently puffed into shape by gravity and motion. Solar flares can disrupt technology on Earth. Solar flares are sudden, powerful bursts of energy from the sun's surface, often tied to sunspot activity. These eruptions release intense radiation across the electromagnetic spectrum, including X-rays and ultraviolet light. When aimed toward Earth, they can disturb the upper atmosphere, affecting GPS, radio communication, and satellite operations. In extreme cases, they can trigger geomagnetic storms that may damage power grids. Earth's magnetic field offers protection, but the flares remind us the sun isn't a steady lamp. It's a dynamic, volatile star that sometimes sends ripples of energy surging across the solar system. The solar cycle influences auroras. Auroras, the shimmering curtains of green, red, and violet near Earth's poles, form when charged solar particles interact with Earth's magnetic field and upper atmosphere. These displays become more frequent and more intense during periods of high solar activity, which follow an 11-year cycle. During solar maximum, increased sunspots and solar eruptions send more particles streaming toward Earth, fueling brighter auroras. During solar minimum, the lights are calmer. The sun's magnetic fluctuations ripple outward, and we see them painted across the sky, a reminder that space weather can brush the heavens with solar light. Comet tails always point away from the sun. As a comet approaches the sun, its icy surface begins to sublimate, releasing gas and dust that form a glowing tail. But the tail doesn't trail behind like smoke behind a train. It points away from the sun, no matter which way the comet is traveling. That's because solar wind and radiation pressure push the material outward, forming two distinct tails, a curved dust tail and a straighter bluish ion tail. The result is a luminous, windswept signature that reveals the invisible force of sunlight through the darkness of space. Some planetary moons formed from giant impacts. Earth's moon is thought to have formed from a colossal collision between the young Earth and a Mars-sized body more than 4 billion years ago. The impact blasted debris into orbit, which gradually gathered into the moon. Similar origins are suspected for other moons, such as Pluto's Charon. These violent births contrast with captured moons in the outer solar system, showing that no single process explains all satellites. Some moons were forged in fire and collision. Others were gathered by gentle gravitational snaring. The variety of origins reflects the chaos and creativity of the solar system's formative years. Voyager 1 carries a golden record into deep space. Launched in 1977, Voyager 1 now travels through interstellar space farther from Earth than any other human-made object. Mounted to its side is a golden record, a phonograph disc containing sounds and images chosen to represent life on Earth. It includes greetings in dozens of languages music from around the world, and recordings of waves, birdsong, and laughter. Designed by a team led by Carl Sagan, the record is meant for any intelligent beings who might one day find it. It's a message in a bottle cast into the galaxy, a quiet greeting from our pale blue dot. Earth shares its orbit with orbital asteroids. Although Earth circles the Sun on its own path, it shares its general orbital neighborhood with small bodies called co-orbital asteroids. These objects don't orbit Earth like moons. Instead, they follow stable looping routes near Earth's orbit, shaped by gravitational interactions. Some, called Trojans, hover near stable Lagrange, points ahead of or behind Earth. Others trace horseshoe-shaped paths that keep them nearby without colliding. These companions are often temporary, captured and released over thousands of years. Invisible to the naked eye, they drift near us in space, fellow travelers on our yearly journey around the Sun. Neptune was once confused with Uranus. Before Neptune was officially discovered in 1846, some early astronomers may have seen it without realizing what it was. Because it moves so slowly and looks so dim, it was sometimes mistaken for a fixed star or assumed to be another sighting of Uranus. Galileo may have unknowingly observed Neptune through his telescope in 1612 and marked it as a star. Only later, when mathematicians noticed irregularities in Uranus's orbit, was Neptune predicted and then confirmed. In a sky full of wandering points of light, Neptune stayed hidden in plain sight for centuries. The edge of the solar system isn't defined by gravity. The Sun's gravity reaches far beyond Pluto, holding distant comets and icy bodies in the Oort cloud. But when scientists talk about the solar system's edge, they often mean the boundary of the heliosphere, where the solar wind meets the interstellar medium. This frontier, called the heliopause, marks the point where the Sun's magnetic influence and particle flow fade. Gravity continues far beyond, but the energetic boundary is where the space between stars truly begins. It's a subtle, shifting border, more a change in pressure than a change in presence. Planetary atmospheres slowly leak into space. Even thick atmospheres like Earth's are not permanent. Over time, light gases such as hydrogen and helium can escape a planet's gravity and drift away. This process, atmospheric escape, is stronger on smaller planets with weaker gravity, such as Mars and Mercury. On Venus, the lack of strong magnetic shielding has allowed solar wind to erode parts of its upper atmosphere. Earth loses thousands of tons of hydrogen each year. Though it's easily replenished, the slow loss is a quiet leak into the void, a constant exchange between planets and the vacuum beyond. Some moons may have formed from ring systems, just as rings can fade into planets or disappear over time. They can also create moons. In Saturn's case, it's possible some small outer moons originally formed from ring material that clumped together beyond the planet's Roche limit, the distance where gravity can gather matter into moons rather than tear it apart. Moons like Pan and Daphnis, which orbit within Saturn's rings, may still be accreting material today. These moonlets act as quiet sculptors of the rings, their gravity carving gaps and waves into the icy bands around them. Voyager 1 is still sending data from interstellar space. More than 45 years after launch, Voyager 1 continues to transmit faint signals back to Earth as it travels through the interstellar medium, billions of kilometers from home. Its instruments measure cosmic rays magnetic fields, and plasma density in the space between stars. Power is limited and systems are gradually shut down to conserve energy, but the spacecraft still operates. It runs on a small nuclear power source and communicates through the deep space network. Each signal takes more than 20 hours to reach Earth, a whisper from the edge of human exploration. The solar system completes a galactic orbit every 225 million years. While planets circle the sun itself is also moving, revolving around the center of the Milky Way. It takes roughly 225 to 250 million years to complete one orbit, sometimes called a cosmic year. During that time, the solar system drifts through changing regions of interstellar space, potentially passing through galactic arms, star-forming zones, and clouds of gas and dust. This motion may influence comet activity, and over longer timescales, even Earth's climate. We are not fixed in space, but part of a vast, slow spiral, riding the galaxy's arm like a cosmic carousel. And so, our quiet journey through the solar system comes to a gentle close. From the inner worlds scorched by sunlight to the icy moons that whisper in the dark, we've wandered together through orbits, storms, and shadows, one sleepy fact at a time. If your eyes are already heavy, that's perfectly fine. Let the last traces of starlight fade behind your thoughts, and let your breath carry you softly into rest. There's still so much more to discover, but for now, you've learned enough. You've traveled far, and the universe can wait until morning. Thank you for spending this time with me. And under the quiet stars, the story goes on. I hope you sleep well and dream gently. Good night.